So in this tutorial I want to cover how to perform simple electrical simulations in OghmaNano. So if you haven't got the software already, you can download it from oghmanano.com/download.php. If you've got bugs, please report them to roderick.mckenzie@durham.ac.uk. So in this little talk I'm going to be covering making a new simulation, defining device layers, editing the electrical parameters of the material, and systematically varying parameters over a range and plotting results. So this is the type of thing you might want to do if you've got a device, you want to understand how, say, mobility affects it, or how layer thickness affects it, or sort of systematically vary simple parameters. So I've covered this before, but I think it's good to say it again. Once you open the software, you'll get this presented with this window on the left. You click New Simulation, and then if you click this, double click on this solar cell, it will give you it'll ask you where to save it, and save it to somewhere local with fast disk access. I would avoid saving it on a place like OneDrive or Dropbox, because the network access will slow down the simulation when you run it. This is one of the most simple types of solar cell that you can simulate with this model, and we're just using it here because it's sort of a nice, simple lead-in example of what to do. If you want more advanced, more modern solar cells, they're in the organic solar cell folder there. So once you've opened that, click Run, and then the simulation will run. Navigate to the Output tab, and if you double-click on jv.dat, you'll be able to see a current voltage curve have been generated. So now we're going to look at defining material layers. So this is the simulation that you would have opened, and this device has got various layers. It's got ITO layer, a P.PSS layer, a P3HP PCM layer, and aluminium contact. So the ITO and the aluminium are effectively contact layers. The P.PSS is a buffer layer, and the P3HP PCM is a semiconductor active layer. If you click on the layer editor, you get this window up, and there's various columns in this editor defining this device. So you've got the layer name here on the left hand side. Now this is just an English name. You can call it whatever you want. You can call the first layer Bob or Fred instead of ITO. It's up to you. It's just for the humans to understand what each layer is. And then you've got the thickness of the layer in meters. So this P3HP PCM layer here is 220 nanometers, but obviously we're written in meters. And then the optical material, this doesn't affect the electrical properties of the layer at all. So this is just selects the NK data. And it goes to materials database. And we've got the layer type. So the layer type can either be a contact layer, which is obviously a contact to the device. It can be other, which means it's not a contact layer, or it can be active. An active layer is a layer that you solve the semiconductor drift diffusion equations over. So only select a layer as active if it's a semiconductor layer in which you want to solve all the semiconductor equations. So there's a little summary of that, as I said. So you've got layer name, thickness of the layer, optical material, and layer type, which can be contact, other, or active. So here's this little summary table. So if a layer is active, you're solving effectively the semiconductor equations, and in none of the other layers you're solving the semiconductor equations. And if you look on this right-hand side, the optical model is solved over all of these layers. So the sort of distribution of light is solved over those every layer you define. Now it's quite tempting when you start to simulate devices to think that every layer should be an active layer, including sort of buffer layers and contact layers. It's not necessary. Generally speaking, it's only necessary to make the semiconductor layer active. Right, editing the electrical parameters of material. So there we've decided which are going to be our electrically active layer. So if we now click on electrical parameters, you'll get this window up, which describes effectively the electrical parameters that define or are used by the model to simulate the layer. So you've got various things like electromobility, hole mobility, effective density of states, recombination rates, trap densities. So we're going to have a go at editing the trap density. So here's the electron trap density, here's a hole trap density. So there they are. If you edit those values, say set them to, I think I've said set them a bit smaller, you can click Run Simulation, and you'd have a look at jv.dat again and siminfo.dat. Siminfo.dat, it has things like fill factor, JSE, and efficiency of the device outputted in there. And you play around with these values, try setting them, I don't know, to 10 to 20, 20 to 24, 20 to 22, and rerun the simulation a few times, so we'll just get a feel for how that changes the current voltage curve, so how it changes this curve here. and there, where's the siminfo.dat? I think it's actually hiding. I think it's under here, but there's, or is it? No. So you'll see in there it's also spitting out a siminfo.dat. Okay. Now, yeah, there's the contents of siminfo.dat. So there's fill factors, power conversion efficiency, VOC. So all the parameters you'd want from a device. So now we're going to cover systematically varying electrical parameters over a range and plotting the results. So quite often you might say, okay, well, I've got this value of electrical mobility, so electron mobility, and I'd like to see what happens as I change this over 10 orders of magnitude or something. What happens to the current voltage curves? So you can do this using this parameter scan tool. So if you click on the parameter scan tool and you click new scan and type in, say, scan 1 and click OK, you'll get this scan icon appear. And if you double click on it, you'll get this window. And you get this window appear, and in there, if you press the plus button, so you get an extra line added to it, and it'll say select parameter 00 and scan. So what we're going to do is we're going to click on select parameter. You might have to highlight this line for it to work. That's sort of an oddity. You just have to click on the line to make sure it's highlighted. But if you click these little dots, then it'll bring up this window. And what you can do is here you can select basically any parameter in the whole model, and you can select how it's going to be changed. But in this case, we're going to select epitaxy, P3HT, PCBM, drift diffusion, electron trap density. So we're going into the layer structure, the active layer, then changing drift diffusion parameters and electron trap density. So you highlight it there so you can sort of navigate your way down here, click on that and click OK, and then it should read like this. Make sure this is set to scan, which it should be, and then enter these values into this box here. So you want 1e to 24 and a space, 1e to 25 and a space, and 1e to the 6. So we're entering 3 values. Okay, and it should end up looking like that top line there. Then click the plus button again, and you should get another line down here. If you highlight this line at the bottom and click on the dots, you'll be able to select again, and this time we want to select in this window, we want to select hole trap density. So let's go back. So you want to make this line here read hole trap density, and you play around and make it look like this. Okay. Now what we're going to do is we're then going to click on this bit here. So the bit on the right with the under operation, and we're going to set this here to epitaxy, P3HT, PCBM, drift diffusion, electron trap density. And what it's going to do is going to duplicate, the word duplicate will appear here. Now what this is doing, so I'll explain what this is doing. We're effectively saying, okay, we want to vary the electron trap density from 1 to 24, 1 to 25, 1 to 26 meters, so it's a density, so it's meter to minus 3. And scan means we're going to run 3 simulations, one with each one of these values. And then what we want to do is we want to make the hole trap density have exactly the same value as the electron trap density, so we're very symmetrically. So to do that, we just select that this parameter effectively is going to follow this previous parameter. So we just make sure that this parameter on the top left is in this parameter on the bottom right. So this and that should match, and then this will vary the parameters symmetrically. So once you've clicked run scan, so I'm not sure I've got a bit, yeah, so then click run scan up there, and once you've done that, click on the plot icon there, and then this window will appear, and click on 1 to 24 and then select jv.dat, and you can select any file you want. But if you click on this plot icon, select one of your simulations, and then click on, say, a file like jv.dat, and then plot this out, all these simulations out together. And you can see we've got a new directory here actually, so this is where we're running it from. I'm running it from Oghma 8.0 / scan 1, and in there it's made 3 directories, 1 to 24, 1 to 25, 1 to 26, each corresponding to these values there. And then when you click on jv.dat, it'll plot out these things together. So that's it really. I've covered making new simulations, defining device layers, editing electrical parameters of the material, and systematically scanning parameters. So I hope that was a useful tutorial, and I hope you find it useful. Thank you very much.